Thanks.
Okay, so let's get back to work. Let me start with some recap and tying up of a couple of loose ends. So last time I tried to persuade you that the ground state of a 1 + 1 DCFT welcome. So last time I tried to persuade you that the ground state of a 1 + 1 DCFT satisfies this equation, which where A, B, and C are three adjacent intervals. Eta is the cross ratio of these 4 points. Psi is the ground state. And delta hat and I hat are various combinations of entanglement Hamiltonians of single intervals. So this is equal to KAB plus KBC minus KA minus KC. And this is equal to KAB plus KBC minus KB minus KABC. And, okay, and let me call this whole thing, so I don't have to keep writing it, I don't know, let's call it K delta. Okay, and this is, so first of all, this is a locally checkable condition in the sense that, yeah, so this is locally checkable. So this is the kind of condition that I was asking for as a possible condition that can characterize the reduced density matrix. And so what I mean by locally checkable is that this is true if and only if this is true, where rho is the reduced density matrix of ABC, where so that is, you can check this equation without knowing the whole wave function. You just need to know the reduced density matrix. So we can hope that this is the condition we were looking for to characterize a density matrix as the ground state of a CFT. So we have a name for this equation, which is vector fixed point equation. The word fixed point here is here as a partial admission of failure in the goal that I just said. That is, there are states that satisfy this condition that are not ground states of field theories whose correlation length is infinite. So there are also zero correlation length fixed points that satisfy this equation. And the word vector is to distinguish it from this equation, the operator version of the equation, where we don't act on the state, which is seems like a much stronger condition, and while indeed is numerically less robust, it's less true in a finite dimensional regularization of the QFT, but maybe it's worth mentioning. Okay, this is a parenthetical aside, a brief interlude in algebraic field theory. In field theory, in the continuum, the vector fixed point equation actually implies the operator equation. It actually implies that K delta is proportional to the identity. And the reason is that in a field theory, the vacuum is cyclic and separating, and that means that if I act with some operator O that lives on the complement of ABC, well, so for any O acting on ABC, well, obviously it commutes with an operator that's supported on only ABC, and the set of states O acting on the ground state is dense in the Hilbert space. And so the Riesz-Leiter theorem implies that, the fact that K delta acting on O psi is proportional to psi, then implies the operator equation. Yeah, implies this K delta is proportional to the identity. Okay, so that's the end of the interlude here. And I mention this just to say that there's a sense that which, at least with some extra assumptions, the vector version of the equation, which is obviously a consequence of the operator equation, is actually not that much weaker. Okay, so that's the end of it. Yes, please.
So how should we
use this equation? Is it?
That's the subject of today's lecture. Yes.
Yeah. Okay. So do you imagine you have like a concrete setup where you have a way to really read off this reduced density matrix and test this, or is it more like just a starting point for formal developments, or both? Or
well, great. Yeah, great question. So I do think both, but in fact the developments that I want to describe to you are in the former category. That is, we're going to think about a finite dimensional Hilbert space, and we're going to look for states that satisfy the finite dimensional version of this equation. Yeah.
Okay. Thanks.
I beg your patience a little bit, and I hope to convey at least some ways in which we can use this equation usefully. Okay. So
sorry.
Yeah.
How seriously should I take this note? Because this K is sort of a regulator-dependent thing, and now you're appealing to Schlieder theorem, which and cyclicity and separating.
I defer to your wisdom about how seriously you should take it.
Okay, thank you.
Yeah. Right. It's think of it as a hint about how about the relationship between the operator version and the vector version. But you can you know what's involved in using this theorem. I personally actually I have to say I really hate the Schlieder theorem. I think it's a sign that we're doing something wrong if we have to use it. But okay, So this is it's a very nice condition. It's locally checkable, and moreover, as Balt was just reminding us, and is cutoff independent, right? So it has a chance to be, it has a chance to exist independent. How do you spell this word? Okay, let's just end there. It has a chance to be something that exists in the sense of algebraic field theory. Oh, and which reminds me, okay, good. So one of the loose ends I wanted to tie up was, so this maybe implies that it exists according to these folks that we were talking about yesterday. And I made a claim last time, exactly related to this claim, that the sentence, say rho does not exist. I said that I think that what this means is when algebraic field theorists say the sentence, what they mean is that rho depends on the cutoff, on the UV cutoff. And Balt had a question about this, but was too polite to ask, or maybe it was too eager for me to get to the good stuff. And the question that he wanted to ask was about really an implicit assumption that I was making when I said this. Okay, maybe I don't know how implicit it was, but I was working in the world where the following statement is true. Let me just write it as a belief, namely that all quantum field theories can be realized. Let's say can be regulated in a tensor product Hilbert space. A tensor product over space. And so this, so let's examine this belief for a minute. So let's think about some possible exceptions to this belief. So one exception that I think is what Balt had in mind is well, here, let's ask whether gauge theory could be an exception to this. So it's definitely true that the Hilbert space of a gauge theory, literally a gauge theory, where the Gauss's law is imposed exactly, is definitely not a tensor product. However, in this regard, I think it's very important to point out that gauge theories can be realized as the low energy description of a system which does live in a tensor product Hilbert space. So this is the basis of the existence of the phases of matter called spin liquids, quantum spin liquids. What that means is that at low energies, it's described by a gauge theory, and there's a very visceral way to understand how this idea is implemented. The idea is just that the Gauss's law condition is imposed energetically, so there's a term in the Hamiltonian. So this is energy. There's some energy scale below which. So here the thing is just some stupid lattice model that nobody here will care about, and down here it's a gauge theory. And so for example, let me just write a very explicit example, which is the toric code. So the toric code lives on, the degrees of freedom live on the links of an arbitrary cell complex. The Hilbert space is a tensor product over links. On each link, there's a two-state system, a single qubit, and the Hamiltonian is this term gamma, this is some energy, times the sum over vertices of, on each vertex, we multiply the product of the sigma z's. Z means sigma z. And then we can add whatever other terms we want. For example, we could add some other energy, which is the plaquette term, the usual Hamiltonian of the lattice gauge theory. X, 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 X. So you recognize this first term as exactly the Gauss law condition in Z2 gauge theory. In Z2 gauge theory, the Gauss law condition is that the product of the gauge fields at each site should be 1. This is like, some discrete version of the flux going into the site. And so you see, think about the regime where gamma is much bigger than J, so that there's this, range of energy scales where the physics of this term lives in a Hilbert space where we impose this as a constraint. Okay, so gauge theory is not an exception to this belief.
But actually, you don't even have to do that, right? Because just the second term commutes with that operation of flipping the spins at...
You're right that these terms all commute with each other. I'm not sure how important that is for the point I wanted to make.
So it's like doing that, you could also just say go to the sector where measuring the charge, the Z2 charge at every site is 0. So there's an infinite number of commuting quantity operators with the other Hamiltonian, so it's just one sector of the full theory.
You could think of it that way. It's difficult to think about the non-abelian case that way. In the case where the Gauss law constraints don't commute with each other.
Well, they don't commute at the same point, but different points still commute with each other.
Okay, I think you're agreeing with me.
Yeah.
Okay. Yeah, good. So I claim that gauge theory is actually not an exception to this belief. A second possible exception one might want to think about is field theories that have gravitational anomalies. But there's a very nice paper by Hellerman and Orlando and Watanabe that shows that a theory with a gravitational anomaly, that it shows that a theory with a gravitational anomaly, there's an obstruction to factorizing the Hilbert space in the same number of dimensions. So for example, chiral CFTs in 1+1 dimensions, or the all-fermion electrodynamics in 3+1 dimensions, or the 2-0 theory in 6 dimensions. These are theories that are exceptions to this statement, at least if you demand that the tensor product Hilbert space lives in the same number of dimensions. And so physical realizations of chiral CFTs, as I hope to say a little bit later, all occur they can occur in some finite dimensional Hilbert space, which is at the edge of a 2+1 dimensional theory. So there is a tensor product Hilbert space that just lives in an extra dimension. Okay, and I don't know any other exceptions. So quantum gravity is not field theory. That's a totally different thing. If anybody knows any exceptions to this belief, please tell me. Okay, so this is the premise of the whole thing I want to say. So we're going to search for CFTs in a tensor product Hilbert space, and if there are CFTs that can't be realized that way, we won't find them. But I personally don't think there are any. What do you think? Do you think there are any? I think probably not. Okay, good. So the other loose end that I wanted to tie up is, I'm sorry? Wow. Okay. All right. I have to say one more thing that is definitely not philosophy, which is I have to correct an error that I made yesterday, which is so in the direction of becoming more concrete, I said last time that if we divide up the circle in parts whose size is some finite fraction of the circle, let's say L is the radius, I said that if we compute the error, so think about the critical transit field Ising model on some chain of length of order L. I said that if we compute the error of this equation as a function of log of the error, let's just say error as a function of log L, that it decays like a power law as a function of the size. And we study this particular example because we're able to do very large sizes without much effort. but I claim that this is a generic phenomenon. And then Joao asked a very good question, which is what happens if instead I fix the sizes of the regions and scale up L. So if I say this is one size and this is another size, and in that case I gave the wrong answer. The correct answer is that actually the error does not decay. Well, I don't know, let's call this L prime is this one. This is L prime. The error does not decay, and Joao gave me a very skeptical look when I said that it did, and he was right. And the idea is basically that the reduced density matrix here is unchanged by making the system larger. Okay. End of erratum. Okay. Good. So the last thing that happened yesterday was that we reconstructed the Hamiltonian. So given the ground state, from the ground state, given a ground state, we can construct an operator, which I call the reconstructed Hamiltonian, which if it lives on the maybe let's say we're living on a circle, it has a preferred normalization, and let me just actually write the preferred normalization. So L here is the number of sites on the circle. I just drew L dots. And the operator is k twiddle I plus 2 minus k twiddle I plus 1. Okay, so k twiddle means I subtract the expectation value in the given state. So this is the entanglement Hamiltonian of 2 sites minus the entanglement Hamiltonian of 1 site summed over all sites with a preferred normalization that's chosen by demanding that that if the formula if this object here satisfies the formula for the entanglement Hamiltonian in the continuum CFT that I wrote down last time, then these numbers add up to So if let's just say if it's a continuum CFT, the normalization is determined so that this adds up to integral dx of h of x equals the CFT Hamiltonian. Okay, so that's how this object was designed. And now let me tell you some virtues of this object. So first of all, it can be written as some positive number, equals some number greater than 0 that I don't remember, times a sum over deltas. It's delta I minus 1, I plus 1, I plus 2. These are it's this object, where now I'm specifying it by where the boundaries are. And the reason that this is an interesting fact is that this operator, so it's an operator made of entanglement Hamiltonians, is non-negative as a consequence of purely quantum information theory considerations. This is a theorem due to Isaac Kim and my student David Lin, and one other collaborator whose name I'm not going to be able to reproduce. So this condition is an operator version of strong subadditivity. It's a stronger statement than the strong subadditivity condition that we used many times in the last 2 lectures. And so you see this operator that we constructed just on an arbitrary state, not necessarily a CFT ground state, is bounded below by a quantity independent of the system size. Right? So it has a good ground state. It has a good ground state. It is bounded below by a quantity independent of L. That's one property. Another property is that, which is more obvious, is that it's a local Hamiltonian, meaning it's a sum of local terms. In fact, it's a sum of nearest neighbor terms. Right? It only ever acts on 2 sites at a time. Right? This acts on one site. This acts on 1 site. This acts on 2 sites. Maybe I'll sometimes write this as K2 minus K1, indicating the range of its interactions. And so the fact that it's local means that, if we reconstruct this operator from a small system, we can find the ground state of this operator on an arbitrarily large system. Okay, and in fact, we can show that if psi satisfies satisfies the vector fixed point equation, okay, so let's say satisfies the fixed point equation, then it's the ground state. Let's say, yeah, then psi is the ground state of the reconstructed Hamiltonian constructed from psi. Maybe maybe sometimes I'll put a little psi there and indicate which state it came from. And actually, one thing I can say that can make this palatable is suppose that there's only 4 sites. Suppose L equals 4, which is a case that we're going to focus on in a minute. In that case, it's not hard to show that this object, k delta, acting on psi. So this is some combination only involving A and B and C. Using the fact that the state is pure, you can replace, for example, you can replace KABC. Yeah, purity implies, for example, that KABC acting on psi is KD acting on psi. You can show that this is equal to the reconstructed Hamiltonian, or okay, it's at least proportional to the reconstructed Hamiltonian acting on psi. Okay. Okay, so now...
Sorry, question.
Yeah, please.
I lost track what this psi is. How do you know it's pure?
Psi, it's a pure state on my whole Hilbert space. That's a key assumption. Yeah, so... Yeah,
I thought we were looking for psi.
Say again?
I thought we were looking for psi. We don't know what it is. Or
yeah, in what I'm saying here, I don't know what it is, but I do know that it's some pure state in the whole Hilbert space, right? So I have a tensor product Hilbert space.
Sorry, how do you know it's a pure state?
That I'm allowing myself to choose it to be a pure state. Yeah, a pure state on the whole system. I'm not interested in mixed states on the whole system.
But maybe the ground state is a mixed state. I don't know.
That doesn't make any sense. The ground state is an eigenvector of a Hermitian Hamiltonian. It's always a pure state. Yeah.
Okay.
Yeah, I'm making many assumptions, but I think that one's okay. Okay. So by popular demand, let me say something about what happens if we do this procedure in an example. So one example we can do is the transversal Ising model, the critical transversal Ising model. And let's think about the critical transversal Ising model on, say, let's think about 8 sites. So actually, you know what, even for 4 sites, I think the resolution of the picture that I'm about to draw will not allow us to distinguish between them. So here's eigenvalue number, and here's the energy. So I'm gonna draw 2 things. One of them, in black, I'll draw the spectrum of the critical transversal Ising model on say 8 sites. So here's the ground state, and then the first excited state has energy 1/8. Right, that's equal to 1/16 plus 1/16. And then there's a state at energy 1, which is equal to a half plus a half. And then there's the descendant of sigma, which is at energy 1 plus 1/8. Sorry, there's 2 of those, right? Yeah, there's 2 of those. And then there's, who's next? Somebody remind me. I think maybe the stress tensor is next, is that right? No, sorry, there's a whole bunch of, there's the descendants of this and the stress tensor at 2. Right, so it looks something like that. So you'll notice that the thing I'm doing is actually just writing the operator spectrum of the critical 1 plus 1D Ising model. And the reason that's the same is because we're on a circle, so we're doing radial quantization, and secondly, actually already very small transversal Ising models actually already capture the spectrum pretty well. Okay, so this is nothing new. But then let me plot the spectrum in blue.
Did you subtract the Casimir energy? Or?
Yeah, I set it to 0. I set I wrote this twiddle thing. Yeah, I subtracted the Casimir energy. Yeah, that's right. So the additive normalization is fixed by that. And actually, good question. So let's say in this plot, I fix the multiplicative normalization by demanding that the stress tensor has energy 2. That the states associated with the stress tensor have energy 2. So the stress tensor has dimension 2. Okay, so but now let me. So so this is some arbitrary microscopic lattice model that people like. But now let me start with its ground state and do this procedure, right? So the multiplicative normalization of the operator is fixed. The additive normalization is arbitrarily fixed so that the ground state is 0. But that's the only it's a 0 parameter fit in that sense. And the spectrum, well, you can't really tell the difference. already, so yeah, maybe for 4 sites you can see a little wiggles somewhere up here, but already for 8 sites, you just can't tell. Okay, so it's really, so the reconstructed Hamiltonian is really very close to the original one, and that's
so the dots are exact and the circles are what you would get if you were simulate this with 8 lattice sites.
Well, okay, so obviously nothing I'm drawing is exact, but what I intended I think at the precision of the drawing, there are 3 things that are on top of each other: the exact spectrum of the critical Ising model on a circle, the spectrum of the transverse Ising model, the critical transverse Ising model in the lattice on, say, 8 sites, and the spectrum of the reconstructed Hamiltonian of the ground state of the critical transverse Ising model on 8 sites. Yeah, you can't see the difference between those 3 things. Okay. At the level of resolution that I'm showing here. Okay, good. Okay, I don't know if Leonardo is going to tell me that this is philosophy, but let me say, okay, yeah, Slava might, yes. There's a what I'm describing here is an exploration of the hypothesis that this condition, this locally checkable condition, is a sufficient condition for the state to be the ground state of a CFT, right? And so, let me try to give some evidence that just this information knows something about at least scale invariance. Well, okay, knows something about conformal invariance and scale invariance. So let me list a few pieces of evidence for that here. So if we use the operator version of the fixed point equation, it's easy to prove by, so that, the key thing about the fixed point equation is it allows you to decompose the entanglement Hamiltonian of a big region into the entanglement Hamiltonian of a smaller region. And so it's possible to show that if I make, so in this construction here, there was a choice of lattice spacing. Let's say, okay, let me say it this way. So I can define HREC2. While you wait for the microphone, I'm going to write this formula.
Here in this game, the reconstructed Hamiltonian still acts on 4 qubits, right? It's the dimension of the Hilbert space of the original model was 2, and in the final model, it's also 2.
Yes, yes. It acts on the same Hilbert space, yes.
And is the Hamiltonian the same?
In general, no. In general, no.
In this case.
I'm pretty sure it's the same in this case, yes.
So then it's not so surprising.
It's not surprising that the spectrum is the same, yes. Yes. Yes, that's correct.
It usually happens. Yeah.
That's correct, yeah. That's usually what happens if you compute the spectrum of the same operator. I agree with you. Okay, so I can define a sort of coarse-grained reconstructed Hamiltonian where instead of using 2 sites and 1 site, I use 4 sites and 2 sites. And using the operator fixed point equation, it's not hard to show that this is twice the original one. If I call it, I don't know, this is H1, the original one. So it satisfies scale invariance with the right exponent. If I double the size, I pick up a factor of 2. And we can also reconstruct by formulae that I will not write the rest of the conformal generators. We can also construct mu nu, p mu, and the special conformal generators, which also satisfy the correct scaling relations if you use the operator fixed point equation. Okay, so to understand a little better what this condition means, let's think about this condition. Here's a useful observation. This condition that the state is an eigenstate of this k delta object is actually the statement that psi is a stationary point of a certain function, which I'll call S delta, which S delta is, it's not a mysterious thing, it's just the scalar, 1 minus eta, scalar version of this object, right? So if I just remove the hats from here and here. That's what I mean by S delta. And at the saddle, so what I mean by stationary is if I vary the state, preserving its norm, this quantity, the variation of this quantity is 0 to first order. So it's a saddle point of this function on the space of states. And at the saddle point, the value of S delta is C, the central charge, H eta over 3, right? The thing on the right-hand side of the vector fixed point equation. Okay, so here's the the conjecture that I'd like to try to defend, or try to give some evidence for. Critical points, so that is critical points of this function S delta, that is states that satisfy the vector fixed point equation, are RG fixed points. And that's the origin. That's why we call it vector fixed point equation. And yeah, so I emphasize it's a slightly weaker condition than saying that critical points are CFTs, because as we'll see, there are solutions of this equation that are not CFTs.
Why are you saying the reconstructed Hamiltonian is the same for the easy model? The interaction range are different.
No, it's two. It's two sites.
It's next to nearest neighbor, and
this is like ZZ plus X. Nearest neighbor. Sorry, I'm using a strange notation where the site is the interval in between the points I'm labeling. Yeah, it's a confusing notation. Yeah, I've messed this up many times myself. Yeah. Okay. So good. Yeah, let me emphasize. So in a finite dimensional Hilbert space, this equation, it's a very strong condition, right? Say the Hilbert space is n-dimensional altogether, so psi is a vector with n components. For each choice of ABC, this is n equations on those components of the n components of the wave function, right? So already there's as many equations as there are objects that we're solving for, but then further, we want to impose this for every choice of ABC. So it's very surprising that there are any solutions at all. And yet in the continuum, we know that the ground state of any CFT satisfies it. So this, I think, this is a way in which CFT ground states are clearly special. And therefore we should hope to be able to find them. Okay, so now, so you all asked many people asked, how do we use this equation? And okay, I don't know what the definitive answer to this question is, but a way in which we can use it is to do the following very crude thing. So let's think about this picture. I'm going to divide space up into just four regions. In the continuum CFT, each of these things is associated with an infinite dimensional Hilbert space. But let me just very rudely replace each of these ABCD with just a single qubit. Okay, so the whole Hilbert space. Yeah, I'm going to think about this picture. It's just a qubit, tensor product of 4 qubits, okay, with periodic boundary conditions. And let's, so we'd like to look for states satisfying the vector fixed point equation, or rather saddle points of this function S delta on the space of states. And we want to look for CFT ground states. CFT ground states are translation invariant. We're going to think about translation invariant and time reversal invariant. So that is, we're going to think about real wave functions in some basis. Actually, if somebody knows an example of a CFT ground state which isn't time reversal invariant in some intrinsic way, please tell me, because then we should, if they exist, we should expand our search. So we're gonna look in some space of states. All right. So this, and this is I think it's 5 real parameters in the case of qubits, right? So this is just some 5-dimensional space, compact space, so for each psi we can compute this function S, and we can look for saddle points of this function. Okay, and David Lynn made a very nice picture of a slice of this. Yeah, so this is some 5-dimensional space. He made a very nice picture of a slice of this function. Okay, maybe I'll try to reproduce it. Okay, in which you can see 5 of its saddle points. It's pretty amazing. 5 of its critical points, something like this. So this is a picture of S delta on this. I don't know. Let's call it M. Give it a fancy name. M. So yeah, here I'm drawing some. I don't know. This is intended to be some picture of this surface, and okay, and it has it has some number of critical points. I should mention that the function S delta is invariant under local unitaries. So if I replace my state with a state that's rotated in a way independently on each of A, B, C, and D, it doesn't change this function. So each of these saddle points is actually the orbit of these local unitary transformations. So they really are all families of saddle points. And that's the reason I was hesitating about the statement that the entanglement Hamiltonian of the transversal model is the same, because it doesn't actually care about this operation. Okay, and so maybe I'll try to reproduce the table. So we reproduce a table of saddle points, and for each of them, we get some estimate of C, right? So the value of this function at, the height of this function is a measure of the central charge. And I guess maybe I should mention that for this geometry where there's 4 equal size intervals, eta is a half, as I'm sure you guys know better than I do. And so this is, this is just some number that we know, and so the height of the function is an estimate of C, which actually seems to always be an overestimate. And okay, so here are the saddle points in order. Okay, we know that a product state is a saddle point, and cat states also are saddle points where C is equal to 0. And the next thing that happens is one at 0.526, which is the Ising CFT. Okay, now you can see that the value of the central charge is a little bit too big. How do I know it's the Ising CFT? It's because from this state on 4 qubits, we can reconstruct a local Hamiltonian and then study on a larger system and reproduce this picture. Okay, the next one is some number like 1.1, which is a W state, which is, that means this. It's a plane wave, which actually Ryan Thorngren and Lei Goya proved that it can never be the ground state of a unique ground state of a local Hamiltonian. But in fact, it's not the unique ground state, because when we reconstruct the Hamiltonian from this, what we find is a state where there's a ground state degeneracy. It's degenerate with the product state, and the gap, as a function of system size, stays fixed. So this is what I meant when I said that not all the critical points are CFTs, or rather, they're not all infinite correlation length CFTs. So this is what I'm going to call a gapped fixed point. Gapped fixed point. The key, maybe the best way to distinguish it from a real CFT is that there's more than one ground state. There's a ground state degeneracy. Yeah, H reconstructed has a ground state degeneracy bigger than 1. I actually don't know. I don't know. So yeah, so if you study the state on a larger, the ground states of the reconstructed Hamiltonian on a larger system, the value of C, you get jumps around as you vary the geometry of the partition. Yeah. So the meaning of this number, somebody tell me what the meaning of that number is. I don't know. Yeah. I think the problem is that the eta is not meaningful in that case. Yeah, let me just say I don't know. Okay, so the next one is at 1.2, which is the XX model. Again, we can reconstruct the Hamiltonian, and it's again a nearest neighbor Hamiltonian, which whose spectrum we can recognize on a larger system. And then at 1.2.
The local Hamiltonian is on the nose, the one of the XX model, or?
It's hard to tell, because the thing I have is some numerical representation of the thing. I don't know the answer. I don't know the answer. it's a numerical representation of the thing, which is well defined only up to local unitaries. So it's a little hard to tell. Yeah, and so these are 2 points along the C equals 1 line. Again, it's an overestimate of the value of C. Okay, and then there's 3 more fake things. There's a thing you could call a ferromagnet, based on the structure of the thing at 3.5, at 4.1. There's the Fibonacci chain. Actually, this one is very interesting. Here, if you reconstruct the Hamiltonian and study it on a larger system, the ground state degeneracy. Let me write it this way: ground state degeneracy of n plus 1, or n plus 2 is equal to the ground state degeneracy of n plus the ground state degeneracy of n plus 1. There we go. Right. So this is a local Hamiltonian whose low energy physics realizes this thing called the golden chain, which I guess Antonio and Juncha know very well. So this is a way so our search has on its own discovered a way to embed that non-tensor product Hilbert space into a tensor product Hilbert space. Okay, and then at 6, and this is really 6, not 6 point something, is the maximum point, which is where the ground state is actually some kind of, it's something like a perfect tensor in the sense that the entanglement is sort of maximal in every channel. And so this is the top of the hill. This height is 6, this is 0. And so you see, we recognize 3 of our friends in this list, and that's it, right? This is a complete list of all of the saddle points. Okay, so it's not a coincidence that the CFTs that we find in this list are ones that have a parent Hamiltonian that's nearest neighbor, a parent Hamiltonian living on qubits that with nearest neighbor interactions. Right, so these 3 have nearest neighbor parent Hamiltonians, because our reconstructed Hamiltonian is always nearest neighbor on whatever the Hilbert space is. And here, the fact that we chose the fact that we chose qubits, makes it harder to find other things. Yeah. Sure.
Just one clarification. Cat states means what here? Cats of product states or what?
Yeah.
Just that one.
No.
And rotations of that one.
Yeah.
And another thing, how complicated is this function? So given this psi, whatever it has, 16 components. It has 16 components or something. Then you have this projection goes on. But then how nonlinear it is? How
nonlinear it is? It has some square roots and some logs. It's not a 6F4. So in that sense, it's not so bad. Yeah, but it is, I think, it's hard to do the search analytically. It's hard to find critical points analytically.
How hard are these numerics?
Oh no, not hard. Yeah. So good. So you can ask how do we find the critical points? And actually, the easiest answer is some combination of gradient descent by the variance. So this is a function which has zeros at the saddle points of this function, and is positive. And Newton's method. Xiang and David spent a lot of time trying to optimize what combination of these things works best. Yeah, Bowen has a question.
John, I might have missed something very basic. So you said in Davis plot there are 5 saddle points, and in your list why there are more than 5?
Wait, where did I say 5? Oh no, I said it's a 5-dimensional space.
Okay.
Yeah. The search in which so here I'm drawing I'm drawing some two-dimensional slice of a 5-dimensional space.
Okay.
Yeah.
So thank you. Yeah. So the actual saddle point is more than 5. So it matches the number in the table.
This is the number of saddle points. Yes.
Okay. Thank you.
Okay. Okay, good.
So in the ferromagnet is also something with 0 correlation length?
Yes. It's and ground state degeneracy. Yeah. I forget exactly what it is. Yes. Okay, good. And so related to this fact about the existence of parent Hamiltonians, I should mention this CD conjecture of Sierra and Latore, I think I got that name right, which is that realizing a CFT in a lattice model with a CFT in no real, because of my assumption of time reversal invariance. Because I assume that it's time reversal invariant, it's real. Yeah. Did I get the number right? Okay. You can figure it out. Yeah. I think it's 5. Counting, I'm fixing the normalization. Yeah. Realizing a CFT in a lattice model with nearest neighbor interactions on a tensor product over space of d-dimensional Hilbert spaces requires d bigger than c minus 1. Okay, this is a conjecture that these folks checked in all known examples, and it's certainly consistent with what we find. And here we're using d equals 2. Okay, so yes.
So in particular, we expect that if we increase the number of sites, we should be able to find all CFTs with C less than 1. That's the belief. With still with a
if you only increase the number of sites and keep the 2-site thing, this conjecture suggests that it'll be difficult to find CFTs with larger C. That's right.
And did you go beyond 4 sites and find any new CFT that's not C equals 1/2 or C equals 1?
Well, good. So you see, so there are 2 ways in which we can scale up this operation. One is to increase the number of sites, but as you're anticipating, and this conjecture is suggesting that may not help that much if our goal is to say find new CFTs. The other thing we can do is vary the parameter d. So maintain 4 sites and vary d, and that's what we did.
I'm fine for now for finding just CFTs with C less than 1. I just wanted to make sure that I do find all CFTs with C less than 1 and I don't miss anything. Like if there's any evidence for that I will find all CFTs with C less than 1.
Well, yeah, okay, so we know what are the CFTs with C less than 1, right? Because every unitarity is a very important assumption here. So yeah, the fact that we only find one of the minimal models is, I don't know what to think about that. But there's one other awkward thing about increasing L while fixing D, which is that for 4 sites, there's exactly one vector fixed point equation. There's only one way to choose 3 contiguous intervals and leave one of them out. There's only one condition to impose, which is the same as minimizing the reconstructed Hamiltonian. With more than 4 sites, we're confronted with a choice, right? There are actually many vector fixed point equations. We could divide up 5 sites into 3 things in many different ways. And in fact, I think we can show that no state on 5 sites will satisfy all of those conditions exactly. And so I think the best thing to do for more sites is just to minimize the energy of the reconstructed Hamiltonian. And okay, yeah, my answer is I don't know whether we can whether we find more things that way.
Thanks.
Okay, but the thing we did do is increase D, and so this was for qubits. And for, I guess it's called qtrits, the list that we find. So I'm gonna leave out the gapped states. For qtrits, we find Ising, 3 states Potts, tricritical Ising, and then some more points with C equals 1. I guess what is it? We find some more points with C equals 1, and then there's a long list on the computer in my office with C bigger than 1.
Sorry, this is. What are precisely these CFTs? XX model Eisenberg in the CFT language. That's just a free boson.
Free boson, yes.
Both are the same CFT.
Different radius.
Just different radius of.
Yeah, these are 2 points along the C equals 1 line. Yeah. So here we find some other at some other radius actually, and above C equals 1, where we can hope to find something new, where there.
Find anything on the orbifold line?
Good question. Yeah. So indeed. So at C equals 1, there's a whole moduli space and the Ginzburg archipelago, and yeah. So actually, maybe I should confront this issue right now. So there's some picture of the moduli space at C equals 1 that looks something like this, right? And the thing that we realized here are 2 points, which, okay, I'm going to get them wrong if I say exactly which one it is. But a very reasonable question to ask is, well, what about the other points? And the answer is that, here, let's forget about the orbifold line for just a second. The answer is that if I plot, so here's the radius, if I plot the error, yeah, so, oh, yeah, maybe I should mention, there's a way to realize this family of CFTs on a lattice, which is just the XXZ model. So as I vary this parameter delta, so in some range of values of delta, it flows to C equals 1 with some radius. This is some r of delta. And I can study the ground state of this Hamiltonian. It's on qubits still, and compute the error as a function of the radius. And so here's the self-dual radius. And the statement is that the error, I don't know, it does something like, crap. It's something like this. Yeah, something like this. So for in the qubit case, so there's minima of the error. So here I'm drawing the error of the ground state of this Hamiltonian. So it's minimized at these 2 points, this point and this point. When r grows or shrinks, it blows up. One way to think about that is in this regime of large or very small r, there's a primary of very small dimension, which isn't going to fit in this tiny Hilbert space. And in between, where in the thermodynamic limit, these should be marginal, there's a bump, which is some finite size effect. Okay, so yeah, so I claim that as you increase the local Hilbert space dimension, you'll find better and better approximations, which will eventually converge to this moduli space. And so indeed, so Leonardo asked about the orbifold line. So there's the orbifold line over here. The error actually never goes to 0 along the orbifold line, but you can see that it's small. So indeed, we can see some sort of ghostly avatar of the moduli space if we look for states that have low error. Okay, good. We have not yet found the Ginzburg archipelago. Okay, that's a good challenge, I think. Okay, so already with Q-trits, though, you see we find 2 more unitary minimal models. Still not all of them. So I guess I can prove that we can't find all of them because this is it's some relatively nice function on some compact space. It can only have finitely many saddle points. Yeah, so we definitely can't find all of them in for any finite d, but we find more of them. And then so yeah, I guess I should say this. For C bigger than 1, there's no classification of CFTs. We don't know what there is. There's the list of what we know is in the new paper by Antonio and Junchen, and there's no known CFT between C equals 1 and, what is the best number, 1.15? 1.14, okay, I was close. Yeah, so in our list here, what I mean by more is a list of saddle points with some estimated values C, which is not very good, which unfortunately at the moment we still have to by hand go through that list and reconstruct the Hamiltonian and look at the spectrum and try to identify it with some known CFT, or if we can't, you have to try to figure out what it is. So that we're still working on it.
but you can tell whether the correlation length is 0 or infinity.
Yes, that's right. So the easiest check is whether or not there's a ground state degeneracy. That's right. So we can. It's not hard to tell whether it's a CFT or not, but it's a little harder for us to tell which CFT it is. So yeah, so we're going to spend a lot of time with Antonio's list. Okay, and I think notice that there no input into this discussion had anything to do with rational, right? So I think maybe we'll find the one that you found. We can hope maybe we'll find something new.
Just with 4 sides, when you plot the spectrum like you did in that plot over there, does it also match to the precision of this?
I think it goes wrong. It goes wrong a little earlier. I think maybe in this picture you can already see some wiggles, but we don't need to restrict ourselves to 4 sides, right? Because once we find the state, we know the local Hamiltonian. We can study it in a larger system. Eventually, we'll have to do DMRG to get a better estimate of the central charge. yeah, we can tell what it is, right? Okay. All right, so maybe I should mention just a few very practical things, even if you don't think we'll find any new CFTs because you think we know all the CFTs already for some reason. I don't think anybody could think that. This is a very useful tool for finite size numerics. So one important point is that the fact that this multiplicative normalization is fixed out of the box means that so I said when I wrote the transfer field Ising model, the way we fixed the multiplicative normalization was finding the 1, 2, 3, 4, 5, 6, like the 7th state in the spectrum and setting its energy equal to 2. Right? The stress tensor is generally not very low in the spectrum because most CFTs are not sparse. And so this is not the easiest thing to do. And so you just don't need to do that anymore. Right? Just find the ground state, reconstruct the Hamiltonian, and the normalization is fixed already. So that's one very nice thing. Another very nice thing is that it's not very hard to compute this error of the vector fixed point equation. And so if someone hands you a Hamiltonian, say in 1 + 1 dimensions, you can just draw the phase diagram. Suppose it has some parameter, and the error of the vector fixed point equation will have some plot like this, and you see, look, there's two phases separated by a critical point. It's very easy to make some very quickly make plots of the phase diagram. I think it. Oh, sorry. Yeah, I was just mentioning that this object, the error of the vector fixed point equation, is a simple, perhaps somewhat coarse, diagnostic of the topology of the phase diagram of a given lattice Hamiltonian. So suppose someone hands you a Hamiltonian of some local Hamiltonian in 1 + 1 dimensions with some parameters. I recommend that one of the first things you should do is, for each value of the parameters, plot the error of the vector fixed point equation, and the minima of that quantity identify fixed points. So either gapped fixed points or CFTs separating phases from each other. It works very nice. So I have some notes with some pictures, which okay.
Sorry, John.
Yeah.
How do you? So Joao asked a question about the spectrum, and I guess you can ask, how do you get more precise estimates of the spectrum?
Yeah, just so take the local Hamiltonian and make the system size bigger.
But you have to tune the couplings to the critical point, right?
Tune.
Because you get something.
There's no tune.
But you get something numerical, right?
Yeah.
It's not exact. So at some point you're going to run into trouble. You're going to have to tune your couplings, right? Your Hamiltonian is not exact. It's numerical. So by construction, it's not tuned to the critical point.
Okay, you're worried about drift of the critical point as a function of system size?
Should be contaminated by relevant operators.
By relevant operators?
By relevant also. Relevant operators.
Well, okay. I mean, yeah. The thing we're trying to do here is minimize the coefficient of the relevant operator, right? That's the goal. Yeah. I mean, it's true. I'm doing something numerical.
If you're given there's a procedure that gives me a Hamiltonian, a local Hamiltonian, right?
Yeah.
Now I say I build it out to an arbitrarily large number of sites, but this Hamiltonian is not exactly at the critical point. Because it's a numerical, right? There are numbers in there, they're floating point numbers, so it's by construct. So at some point it's going to flow away.
Okay.
Right?
Okay.
So there's an upper bound to how precise you can get the spectrum.
I see. I see what you're saying.
I was
saying, yeah. So right. So you're right. So okay. Someday when we're very powerful and we're doing studying matrix product space with a gajillion sites, we'll have to use arbitrary precision calculations when we minimize the error of the vector fixed point equation on the small system.
No, it's not that.
Yeah.
It's really the fact that your Hamiltonian is not the right Hamiltonian that flows to the critical point, because it's a numerical thing, right? Why is it exactly the Ising Hamiltonian?
That's some accident of the Ising model.
Or why is it exactly the tricritical Ising? To reach tricritical Ising, I have to tune a lot of stuff.
Right? No, good. We have to tune two things. Yeah, by definition. But hold on. So.
Well, in your case, even to reach Ising, I need to tune two things because I'm not sure about the Z2 symmetry.
Right? No, that's right. There's no. Yeah. No, okay. I'm not sure I understand the content of your question, but let me say. Okay, so I think maybe there's some presupposition in what you're saying that the lattice model that somebody wrote down, that Ising or his advisor wrote down, is somehow the right Hamiltonian, right? It's it's some arbitrary human-based thing that they wrote down some particular interactions, which happens to at some point in its parameter space hit a representative of this universality class. If you believe the things I've said, solving this equation, finding a state that's a saddle point of this condition is a more intrinsic notion of finding the fixed point than any Hamiltonian that somebody wrote down. And I claim that compared to some Hamiltonian that somebody wrote down and found some critical point of, the reconstructed Hamiltonian that we get, but starting with the ground state of something that someone gave us and reconstructing the Hamiltonian, I claim that it's a better approximation in the same Hilbert space to the ideal CFT Hamiltonian. Okay, no. Yeah. Okay.
I think Balt has a very good question. Maybe it's just a misunderstanding. So if I do this exercise in four sides,
yes,
I get some Hamiltonian.
Yes.
Okay? Now, do you claim that if I take this exact Hamiltonian and I put it in L sides and I send L to infinity, I am exactly at the
No, of course I agree that there's some
okay,
numerical
I
error.
think that was the question.
Yeah.
So you have to improve the Hamiltonian with more equations when you go to bigger length.
More equations, I don't know. No, I mean, it's a local Hamiltonian, right? The Hamiltonian is determined by the information, the local information.
But it's not enough to determine it with your four-side initial equation. That determines a...
Yes. Oh, yes. I should have said that. Yes. The value of the central charge here is, I don't know. Okay, I forget what it is, but it's definitely better. Let's say closer to 0.5.
No, that's not increasing the size. That's increasing
the local
D,
Hilbert space
right?
dimension.
So now take that Hamiltonian and use it to compute the spectrum and the central charge for length 4, 8, and so on. Bigger and bigger and bigger. Is it always becoming better, or does it become better for a while and then it becomes worse because you would have to repeat the exercise with more, bigger sizes and so on?
I'm sure you're right that eventually it'll become worse. We have not been powerful enough yet to see it become worse.
So right now, if you plot as function of size, you see the descendants being separated by one better. Everything is becoming better.
Right. It gets better. That's right. And I totally agree that eventually it will get worse, and then we can increase the precision with which we solve this equation, and it'll delay when it gets worse until a point where nobody can study a system.
The confusion is whether it's precision or whether it is.
Yeah. Okay.
You got two Hamiltonians for Ising, right? So clearly, you already got two answers, right? So if you increase the size, one will be better than the other, right?
That's right. If you increase the local Hilbert space dimension, you can do better. That's correct. Yes. Because that's some coarse graining step. You can think about increasing the local Hilbert space dimension as the same as blocking sites together.
We're trying to understand whether you're making the very strong claim that you have already stumbled, that if you had infinite precision just for L equals to 4, you would have found the perfect local Hamiltonian.
Okay.
Or whether you need to take L equal to 5, L equal to 6, and do this more complicated game of choosing all the possible intervals, and that would improve the Hamiltonian.
Oh, okay, sorry. No, there's another thing you could do. There's another thing you can ask me to do, which is to increase D.
No,
right?
increase D we don't want to do.
Why not? Why not? No,
well,
increasing D definitely improves
it.
it.
For now. But for now, let's just do qubits. And the question is whether you claim that for L that
hold on.
Solve with infinite precision the problem for L equal to 4, you would have found the perfect Hamiltonian, or whether you need to do L equal to 5, L equal to 6, and the local Hamiltonian will get a little better.
I don't intend to do anything with L equals 5 and L equals 6.
But maybe people here want to.
I suspect that if you just stick to L equal 4, there is something badly wrong in your procedure.
Something what?
There's something badly wrong.
Badly wrong. Oh, okay.
And the reason why I suspect this is that in your procedure you are using the renormalization group intuition in a very soft way. But we know that there are some CFTs which have irrelevant interactions which are very strongly irrelevant, like the Ising, where the first irrelevant scalar has dimension 4. And there are other CFTs which have weakly irrelevant or perhaps marginal interactions.
Mm-hmm.
And so if
like
you are
these.
just working on as xy, and if you're just working on 4 sites, even with a gazillion sites per every one of these 4 sites, I think there's just simply not enough room for your microscopic theory to flow to a CFT. So this is definitely going to be contaminated. Your result is definitely going to be contaminated by some microscopic details, and you're not going to be able to recover universal information right on the nose.
Okay. Of course I agree with you.
So
yes, this is correct.
I would
this
say that if
correct.
you ever hope to increase accuracy of your predictions, you have to increase not just D, but also the number of sites.
Sorry, maybe, okay, I was answering a slightly different question.
Yeah.
So of course, when we want to get a better estimate of the value of central charge associated with, so that there's some fixed point associated with this wave function on 4 sites, right? It's just a wave function on 4 qubits. You see I'm labeling it by this fixed point. If I want to learn more about that, of course I need to study larger L. Yes, of course I agree with that. Yes, and of course there are finite size effects, right? This is an example. We only find 2 points on this equals 1 line. These points are supposed to, I know that there's a CFT there, but in this finite size approximation, it's that there's a non-zero error. Yeah, of course this is true. Okay.
So then what is that? So your claim, you claim that you're going to discover the CFTs. You're going to be discovering some shadows of the true CFTs.
Yes.
But you know, the difference between the true CFT and the shadow is just a little bit smaller than the difference between a true CFT and total junk. So you might as well discover some junk on the 4 sites that you will never be able to say if it's just junk or a true CFT. And to see this, you will have to go to more sites. So why not just go to more sites to begin with? Why insist on 4 sites? I mean, this seems to be very stubborn.
Oh, okay. I relent. I won't. I'm telling you what we're doing. I won't insist that this is the only thing to do. Okay, if you think there's a better thing to do, do it. Great.
But I thought that the part with just 4 lattice sites is the part on which we generate some ground state and reconstruct some Hamiltonian, and then you can take one Hamiltonian and do how many lattice sites as you want. And the real question that's still underlying is that Hamiltonian, which you can take to have large lattice sites, is it going to be nicely tuned to the critical point, or you still need to play around with it? I guess that's still the question that people haven't figured out. Yeah. Right. Yeah, detuning,
Okay, my answer to that is just we have not studied large enough systems to see any detuning. Okay, I'm not making a very strong claim about that. Okay, thank you for the input. Slava made a statement here about that there's a small distinction between this and junk. I don't think that's true. I mean, they're saddle points of this function. That's a sharp statement. Maybe you're saying that these things are junk. That I'm fine with that, but we can easily exclude those.
D, you will be discovering more and more critical points.
Yes.
And it's going to be more and more difficult to say which one of these critical points have anything to do with CFTs, and which are just the artifact of the fact that you have which are just cutoff effects.
I'm not sure. Okay, yeah, maybe.
That's my just gut feeling, but okay.
Might be. Okay. All right. So I have 10 minutes left.
I still think the procedure is really interesting, by the way.
Thank you for that concession. Okay. I should emphasize. I think this vector fixed point equation is an interesting thing to think about. What I described here is one possible way to turn it into a bunch of numbers. Maybe there's a different way to do it. Perhaps one that where you know what mistake you're making. That would be great. Okay, so I had some things to say about chiral gap states, which is sort of a combination of the first 2 subjects that I've mentioned. Maybe I'll just advertise one result from that direction, which is, a question that I'm surprised nobody has asked is, I drew some function whose saddle points are related to CFTs, or at least related to fixed points. It's very natural to ask whether this function is a C function, right? How is it related to the RG flow, I think. One thing I can say about it is that in a certain limit, in the limit where the three regions look like this, and the overlap is some delta L, and we moreover assume that the state we're studying is the ground state of a relativistic quantum field theory. This quantity, or a very closely related quantity, if psi is the ground state of a relativistic QFT, roughly this central charge, this C that we compute, is equal to the entanglement monotone of Cassini and Huerta. Really equal, it's the same quantity. Which they proved is monotonic under flow of couplings. Right, so this is a particular notion of monotonic. We only look in the space of ground states of relativistic quantum field theories and ask whether this quantity is monotonic. It's possible to show that if psi satisfies the vector fixed point equation, this quantity is stationary. So this is an additional demand one might want to make of a C function, namely that not only is it monotonic under RG flow, but at a fixed point, it's stationary. And here I mean stationary in a stronger sense than this, not just under variation of the couplings, but under arbitrary variations of the state itself, preserving the norm. So this is, if you like, it's some addition to the C theorem that Cassini and Huerta proved. This C function, by the way, is not equal to Zamolodchikov's C function, which is better in many ways. But then you can ask, well, so this quantity, this function that this function that we're studying it's a function on a larger space, right? So they were studying a function just on the space of couplings of relativistic field theories. This is a function on the Hilbert space, and so you can ask whether it's monotonic under relevant deformations. And unfortunately, on the larger space, it's not hard to construct a counterexample. There's one due to Brian Swingle, which is think about free fermions filling a band that has cubic band touching under a relevant deformation. So this has C equals 1. There's a single Fermi point. Under a relevant deformation, you can split that triple 0 into 3, and now it's C equals 3. And if we study this example, it's just some free Fermi example, we can compute this quantity. Indeed, this C as a function of length, this is length, does indeed do something like this. This is 1, this is 3. At some point it sort of jumps up and then approaches 3 from above. So it is monotonic in a certain sense in its approach to the fixed point, but definitely overall it's not monotonic. So what are some assumptions for this to be an actual C function? I'm not sure. That's the first comment about whether this is a C function. The other thing I can say is, although, as you can see, there's not a precise relation between the Hessian of this function and the dimensions of the operators in the CFT. For example, as you can see, this is supposed to be flat. If we thought that the spectrum of the Hessian was the same as the list of dimensions of the operator, it does seem to be true that the number of downhill directions around each point is equal to the number of relevant operators. So the picture, this is an important picture for trying to understand the space of solutions, because we're doing it by gradient descent by this function, and so this question of tuning that we were discussing earlier, the tuning to the saddle point does actually have a close relation to the tuning to the critical point of the couplings. Okay. So maybe in the last couple of minutes, let me just mention that we can try to apply the same strategy to higher dimensional CFT. So in higher dimensional CFT, I would say a lot less is known. There's no notion of a classification. There's a lot more we can learn. Okay. And on the other hand, we do know that the entanglement Hamiltonian for a round ball in the ground state of a higher dimensional CFD satisfies a very similar formula. So it's an integral over space, or integral over the ball itself, of, again, some coolness function times the energy density plus some C number. Where now, here's the region, and this, I won't write the explicit formula for it, but beta looks like this. It's 0 everywhere except it's quadratic in the region A. And again, we can look for linear combinations of these objects. Yeah, so it's important that, this is a round ball. Round is important. If the ball is not round, in fact, I think that the entanglement Hamiltonian is not a local operator. And again, this follows from the Biesignan-Wickman theorem plus conformal invariance by the same argument that I mentioned in 1+1 dimensions. Okay, so the problem is, the reason that this is a more difficult thing to do, is that in 1+1 dimensions, every ball is round. Right? An intersection of round balls in 1+1 dimensions is again a round ball. But in higher dimensions, as you can see, an intersection of round balls is not a round ball. Okay, so on the other hand, we can look for linear combinations of these objects, of just these objects, which add up to nice things. For example, we could try to add them up to 0. That's how we identified the vector fixed point equation. That strategy actually doesn't, we haven't gotten that to work yet. On the other hand, we can try to get them to add up to 1, which is how we constructed this reconstructed Hamiltonian. And that strategy actually seems to work. So that is, we can try to make a reconstructed Hamiltonian, which has the following form. So we take Ka of some region, let me label it I. So A, okay. I'm gonna think about the CFT on the sphere, because I want the spectrum of my reconstructed Hamiltonian to tell me the list of dimensions, and I'm gonna pick some direction here, and so omega here refers to the origin here. It's this choice of direction, and then I'm gonna choose a collection of regions. So this is A1, A2, A3, up to AK, and then I'm gonna sum over these guys, lambda I, and then I'm gonna integrate over the whole sphere d omega sd. Okay, so you see, if I plug this formula into here, even if I don't do the sum, even if I just have a single one, if I average this quantity over the center of the ball, the contribution to each point to the coefficient of t00 is just 1. And so this, at least if I choose these coefficients right, should equal the, so if it satisfies this formula, we'll get the CFT Hamiltonian. Why do I choose more than one region? Well, it's for the same reason that K delta, this linear combination of entanglement Hamiltonians, is better behaved than the entanglement Hamiltonian of a single interval, because in a regularized version of the CFT ground state, this formula is not exactly true, and the picture, well, let me say it's an empirical observation that the correct picture is that the well-regularized entanglement Hamiltonian differs from this by terms at the boundary of A. And so the goal in choosing these lambdas is to cancel these errors at the boundary of A. Okay, so I guess I'm out of time, so let me just mention that we've thought about various schemes for choosing these lambdas and various ways of checking the idea that this reconstructed Hamiltonian is a useful thing. And I guess there are maybe 3 classes of checks. The first thing is we can approximate the sphere by an icosahedron, which actually is a very good approximation because the subgroup of SU2 that we preserve by doing that, it already has quite large representations, as Slava showed in a nice paper. And so the finite size effects are not so bad, except that it's the only one. There's no way to make it bigger. And the other thing we can do is think about the fuzzy sphere. Now the fuzzy sphere is not exactly a tensor product Hilbert space, but nevertheless it's a finite dimensional Hilbert space where entanglement is well defined. And maybe I'll just say that in both these cases, I'll say there are two things we can do. We can choose these lambdas in some way that we think is good and study as a function of parameters. We can think about, say, I guess the thing we've studied mostly is the transverse field Ising model on these spaces. It has some, there's the transverse field, and we can study the error of this quantity. By the error here, I mean the variance of this reconstructed Hamiltonian. And we can see that it looks like that picture, actually. It looks something like this. It's not quite as good as in one dimension, but there's at least a hill, and something like this, where this point is not so far from the best estimate for where the critical point actually is. So that's one small victory. And then the other small victory is, well, we can make a plot like this. So that is, we can look at the spectrum of the reconstructed Hamiltonian and compare to the spectrum of the original one. And let me just say it does pretty well. So one thing that you might complain about is that from this formula, actually, we don't even know whether this operator is bounded below. And we don't have a guarantee that the CFT ground state is the ground state of this Hamiltonian, but in fact it is. This is a numerical observation. So I'm actually somewhat optimistic, based on this, that we can figure out some sort of best prescription for choosing these parameters to cancel out the garbage, and perhaps we can do some analog of the search procedure that we're doing in 1+1 dimensions, also at least in 2+1 dimensions. Maybe we can find some new CFTs in 2+1 dimensions. Okay, I'm going to stop.
Okay, we're a little bit out of time, but any other questions?
Hey, thank you. I wanted to ask, like, you presented this, you were introduced as a lecture, and then it seems like some of the stuff you talked about were really recent, kind of almost work in progress.
Oh, I should have said the stuff in higher dimensions we haven't yet written up. And
I kind of just want to know, like, what's the timeline from the first developments until what you talk about, and like how big of are you part of a community with hundreds of people, or is it just you and your research group, and like what's the context of this whole research direction?
Oh, okay, I guess I didn't give a lot of references. That's a good point. So there's a number of people who are working on the entanglement bootstrap for gapped states that I spoke about for too long, according to the taste of some people, including Bowen and Isaac Kim, and as of recently, Alexei Kitaev, and Daniel Renard. And so there's some small but I think growing community of people interested in that question, and I would say many of those people are interested in improving things, but people working on the application to CFT is my student David Lin, and myself and my student Xiang Li, and on this problem I should mention also my student Rolando Ramirez Camasca, and as far as I know that's it. There was a recent paper by Yannick Maurice on using related techniques in lattice models. They weren't doing a search, but they're studying very similar observables to the ones I was talking about here. I would say maybe that's it. So okay, maybe there's some opportunity for other people to get involved. Yes. Thank you for the opportunity for me to give references. Yes.
So can I ask so did you explore higher local dimension, and how does the complexity increase?
Yeah, so the complexity of the search is not so bad. I think we can do the search for, I don't know, maybe d equals 5, up to 5, something like that. The bottleneck is identifying what the saddle points are that we find in the search. Yeah, the analysis of the results of the search.
Suppose I'm interested in holographic CFTs.
Yeah,
or
it's going to be a
very
little while.
large graph CFTs.
Yeah.
Can you kind of guide the search because you have the spectrum at the same time, so that you kind of look for the saddle points that are more holographic?
I would love to do that. I would love to do that. I think finding large C will be difficult. I have some vague optimism that maybe we'll find Calabi-Yau sigma models.
Or let's say for fixed C, find the CFTs with largest gap and try to see how that evolves.
That I think we could do, but maybe not for very large C. Yeah, I would really love to be able to do that.
Yeah. Well, John, since I made some critical remarks, I just want to moderate them and say that, okay, since the problem of finding new CFTs is a very hard problem, and we don't have many tools to do this. Also like Balt, I think this is extremely interesting, and my comments were rather in which direction one should move from what you already learned, so to get the quickest to the most exciting stuff.
Okay, thank you.
But, otherwise, I think it's looks extremely promising, and because in condensed matter, people usually take this Hamiltonian out of a hat, and then somebody else takes another Hamiltonian out of a hat. But now, you say, well.
Yeah, that's one thing that I like about it a lot.
Systematic. Okay. Yeah. So thank you.
Thanks.
Okay, let's thank John again for these wonderful set of lectures. with Joao, telling us about Einstein gravity from a matrix integral.
Can you hear me well like this? Is it working well back there? Okay, thank you. It's a real pleasure to speak here at the 15th edition of the Bootstrap conferences. Just for curiosity, I went back and looked at the web page of the first edition in 2011, and I found this great sentence. The main theme is the higher dimensional Bootstrap program, which we foresee is coming back to life. Okay? So clearly, this sentence was not written by me, was written by the other organizers, because I really had no clue about the great developments that would happen since then, or have happened since then. But it's quite remarkable, because I think organizing that 3-day workshop in 2011 might be one of the most important events in my life, given the impact it had in my professional career and even in my personal life. Okay, so it's very important. So to celebrate the 15th edition, I decided to give a somewhat anti-Bootstrap talk. Okay. So I'll explain what I mean by that, but okay, so the motivation is basically the same motivation that brought me to the Bootstrap. So we want to understand quantum gravity. So what do I mean by that? Well, there should be some quantum systems that as you flow to low energy, you get some effective field theory, which is GR plus higher derivative corrections. Okay? So that's how it works in string theory. And if you are an effective field theorist, you're happy. You say, okay, if I have some theory that has a massless graviton, a spin 2 massless particle, then in the IR, so that's massless, so that survives, then I can organize its interactions, and just with the rules of effective field theory, I know that the interactions will be organized by curvature invariance, and you build up your GR, okay. You have to fine-tune your cosmological constant, and that's a problem, but up to that, you'd be happy. But here, I want to address a different question, is what if I want to understand what quantum systems can have that in the IR? Okay? So what is special about quantum systems that have this IR description? And this, I think, we still don't have a good understanding. So for example, contrast what happens with the theory of Goldson bosons. Okay? So some other quantum systems in the IR are described by a massless scalar, which is only derivatively coupled, and we also understand very well the effective field theory. But in that case, we also understand the UV completions. Okay? We know that if we start from either a UV complete QFT or some lattice model, where you have spontaneously broken, where you break spontaneously some global symmetry, okay, you cook up some potential that does that for you, something, you know you will get a Goldson boson. Okay? So we understand what are the features in UV that lead to the IR physics we want. That's, if you want, my dream for gravity. Okay? I can build some system that I understand that, this system has this property, so in the IR it will give me gravity. I think we don't know how to do that. That's my understanding. So what do we know? We know string theory. Okay? It's like God-given examples of systems that satisfy that. Okay? But we don't know how to change these systems, and most ways we change them, immediately we break down, it doesn't get to GR. Okay? So my goal, if you want, is to try to study the simplest system, again, given by string theory, that has this property, and then try to tweak with it, study cousins of the model, and try to see really what's special about this system. So, okay, that's the dream. We're not going to realize it today. Basically, today I will present the model that I think it's better suited for this study, and that's basically it.
So just one more thing to finish this, this brief motivation. You could say that ADS-CFT somewhat solves this problem, okay? And in a sense, it is very helpful because we know, for example, if you want to study gravitational theories in ADS, you can take this bottom-up approach, this effective field theory approach, and you say, let's say very concrete. So let's say you take ADS-3 and pure gravity, and then you have just pure gravity in weakly coupled in ADS-3, and then you say, how can I UV complete that? And ADS-CFT tells you, well, look for a CFT, a 2D CFT, so that's a good quantum system, with some good properties. It will have to have large central charge so that the gravitons are weakly coupled, and it should have a large gap so that you don't have other light fields. Okay? But it ends there. Okay, now you have to go and look for this. I'm hopeful that John will help us in this search, but we don't have any idea if these theories exist and how to build them. Okay? So we just say these words, but it's not constructive. It's not microscopic. So that's why I'm saying this talk is a bit anti-Bootstrap, because I'm really going back to the microscopics, looking again at the particles to see if we can find some microscopic origin for these effective field theories. Okay, any question about the motivation? Nobody left the room, it's good.
So, Joao?
Yes.
I mean, that arrow, it's really like a family of quantum systems normally, right? The arrow from quantum system to...
Yes.
Normally it's like a limit of large n, where you have a family of quantum systems and you take n larger and larger, and then you get your GR.
Right. So another thing that that we need, so in this case of CFT for last central charge, but for sure we need a large number of degrees of freedom, and it's going to be in that limit, some thermodynamic limit or something like that, where we find that. And in the examples we know it's a large n limit, yes. Okay, so I think that's it I wanted to say about motivation. So now let me present you the model. So the model, so I'll call it the simplest model. It's this polarized IKKT. So, okay, IKKT stands for Ishibashi, Kawai, Kitazawa, and Tsuchiya. And so this is a model very, well, I guess 30 years old or something like that. But the polarized is a deformation, a mass deformation that was introduced by Bonelli in 2002, also more than 20 years ago. But it was in some appendix of some paper, and basically it was left there, forgotten, and I want to convince you that that's a very good model to study that we should take seriously. Okay? So what is this model? It's an integral, so it's a matrix integral over, I can try. Now there's a bit of a mixture here. I don't know which ones are good. I'll try several until I find one. Ah, maybe this one is better. Yeah, this one is better. Okay, so what is this model? There are n by n matrices, n by n Hermitian matrices, and there are 10 of them. Okay, so this I runs from 1 to 10, and there are 16 fermionic matrices. So this alpha runs from 1 to 16. Also n by n Hermitian. So those are the integrals you have to do. And then you just have some action, which is that action over there. I don't know. Well, let me just call it S, which I wrote here to save you some time. So it's the usual stuff. So the first line is IKKT. Okay, so these are just gamma functions, gamma matrices of SO10. So the first line is SO10 invariant, and then the mass deformation introduces this parameter omega. So you see there's mass mass, okay, it's a bit of there's a quadratic potential for these matrices, and it breaks SO10, as you see, and also a mass for the fermions. And in addition, there's this Myers term that only involves the first 3 matrices, okay? So I, J, K will run from 1 to 3, and then P runs from 4 to 10.
Sorry, psi is real or complex?
It's also an Hermitian matrix, yeah.
Yeah, but it's not Majorana vial if it's SO10.
Sorry?
It's not Majorana vial if it's SO10. Is it SO9?
Okay, that's a very good point. I didn't want to go into those details. So what you do SO9, so then it's Majorana vial, and then you analytically continue to SO10, okay? So maybe the best way to say it is, you can integrate out, one way to say it, you can integrate out the fermions, and let me say this is just the bosonic part, and then you get here a Pfaffian that depends on X, okay? And this Pfaffian is SO10 invariant, okay? Really as a function of X. So there is a way to keep only 16 components that preserves SO10 like that. Sorry. SO10 at this level here, yeah. Then I break to SO, but the number of components is just, you could just discuss that level of SO10. Of course, here I break it. So let me list those properties. So very good. One property we already discussed. So this is SO3 times SO7 symmetric. Okay. Once you introduce this mass deformation, and in fact, I want to put here together what we usually call gauge symmetry, which is conjugation by SUN. Okay, by SUN matrices. Right. I can send every x to u x u minus 1 and psi the same. Right. That leaves the action invariant. So that's what we call the gauge symmetry in general in higher dimensions. But here we can think of it as global symmetry. That's just a point, right? There's no space or time, so that's it. So this precise deformation is chosen so that you preserve all supersymmetries of same number of supersymmetries. They get deformed by this omega, but you preserve all of them. And in fact, this is the unique deformation that does that. Okay? And if you want to learn more about that, I invite you to come to Adrian's talk tomorrow, where he discusses massive deformation of Young-Mills matrix models in several dimensions, and this is a particular case. Okay, another thing which is nice about this model is that it has 2 parameters, okay, n and omega, and in particular, it has a weak coupling limit. So if I take this omega to be large, then basically this is dominated by the Gaussian terms. The interactions are suppressed. And in addition, we can have a 't Hooft limit. Okay, so we could do a 't Hooft coupling. So here, the 't Hooft coupling is always n times Yang-Mills square. So here, I didn't introduce Yang-Mills, but you can use this omega. It's just a rescaling. So it turns out to be n over omega to the 4th. So if you work in the 't Hooft limit, yeah, should I write this? I don't think this is very important. Yeah, so just to be very explicit here. So if you want to see the standard action to do the large n 't Hooft expansion, you just have to rescale these fields with some powers. So very quickly. And then the action becomes n trace the standard 't Hooft form, right? With, I mean, the mass terms don't have any n or any coupling, for example. But then the couplings, so the commutator square will be multiplied by lambda, and the cubic term, the Myers term, will be multiplied by square root of lambda. Okay. xi, xj, xk. So you can do, well, there's also the Yukawa term. It's also multiplied by square root of lambda. Psi x psi. Okay, let me just write schematically. Okay, so I just want to emphasize that this is really a standard matrix model that has a standard 't expansion if you start from small 't coupling. Okay. Okay, what else do I want to say about this model? Another important property of this model is that it has many vacua. So what do I mean by vacua here? I just mean local minima of the action. Okay. So basically, of course, if you set all x's to 0, that's a minimum. There's no linear term in x. But there's more minima of the form of sometimes called a fuzzy sphere. So if you set all the xp to 0, so the p from 4 to 9, but the first 3 xi, you set it to a representation of SU2. Okay, so ji is an n by n representation of SU2. So if you do that, you see the fact that you have a quadratic term in xi, a quartic, and this cubic, you can form a perfect square that vanishes exactly when x is a representation of SU2. Okay? And in fact, there's many representations of SU2, n by n, because this doesn't have to be irreducible. So you can just take this J to be block diagonal, where you put blocks of irreducible representations, irreps, of SU2. Okay? So in fact, you have as many local minima as partitions of n, partitions of the integer. Okay, so that's richness of this model, but in this talk, I will mostly focus on what we call the trivial vacuum, where I just set all to 0, okay? All the xi to 0. I don't consider these bigger fuzzy spheres. I need to change marker again, maybe.
Can you just throw this out somewhere?
Sorry? Ah, I should separate it, it's true. I put it on this lower drawer. Okay, what else? Last comment. So this is an integral, so why don't we do it? So it's a big integral, right? Because you have 10n square real integrals to do. So when we have big integrals, we do Monte Carlo. Okay? So it's possible to do Monte Carlo, but it's hard because this Pfaffian is real, but not positive, not always positive. Nevertheless, it has been done. So there is a group in India, Kumar, and Joseph, that have done Monte Carlo for this model using what's called complex Langevin, which is a way to get around this sign problem. But, I mean, they didn't go to very large sizes, and it was a preliminary exploration. I think there's a lot of interest in pushing that further, and it's one of the directions we are exploring. I'm surprised there's no questions. I'm usually not as clear as... No? Okay. Everything is clear here. Yes.
The way you... sorry. The integral is a function of omega. That's the non-trivial thing we want to compute, basically. Otherwise, it's just a number. We don't want to compute just a number.
Right, right. So, of course, this is the partition function. But this model has many observables, right? I can consider expectation values of... traces of the x's, let's say, right? X, x, I1, I2, ... and multi-trace if you want. I guess the usual normalization you put here 1/n. So there is many observables that you can compute with this model, right? This is just a partition function, and the question is, if supergravity in principle makes predictions for some of these observables. That's actually a bit non-trivial to identify because the dictionary between the dual and this model is not well established, and we want to understand how come supergravity computes that so well, for example, right? It's just the same as in any other ADS-CFT example. More questions? Okay, so that's the model, and you say, well, there are for sure simpler integrals. Why did you choose this mess? This is the simplest I know that has a gravity dual, okay? That we can build a gravity dual that we can trust, and it's a big parametric region of which is under control, both string corrections and loop corrections in string theory, okay? And now let me just briefly summarize the gravity duals we built for this, okay? So there's some non-trivial geometry, so I won't give you all the details, but I want you to get a feeling that they are very explicit. So yeah, better if I keep the actions. So the dual, essentially, you obtained it with a combination of string theory reasoning and then solving some supergravity tricks. Okay, so what's the idea? Well, we know from string theory that this action, so for example, the first line is just the effective action for n d instantons in R10. So that's what the IKKT does in string theory. It's the effective action when you put n d instantons. And then this deformation corresponds to deforming the background, okay? We're not going to put the n d instantons in R10. We turn on some fluxes, okay? So that's the background before putting the d instantons. So that's going to control the asymptotic behavior of the geometry, okay? So let me just briefly tell you then what we expect for the geometry. So the metric, I will write it in some convenient coordinates. So it's just R10 asymptotically, but I'll take the opportunity to introduce. I'll write R10 as R3 plus R7, because that's the convenient symmetry that is preserved. Sorry, R squared, d omega 6 squared. Okay, so this is R7. Plus subleading terms, okay? Okay, so this R is just the overall R, z squared plus rho squared, the overall radial coordinate in R10. And then it's also important that we have this axi-dilaton, okay? So there's a dilaton. This is just the usual combination of the dilaton and the axion. And then there's also Ramon-Ramon three-form flux, and that's the actual important guy, which is proportional to omega and is a volume form on R3, okay? So you can write it as like that, dz d omega to, yeah. Okay, so this is the volume form on R3. Okay, so if you want, that's the background. Sorry, I should also write this one. So there's here some subleading terms. And here you see there's a quadratic plus subleading terms. So this is if you want the background before putting the d instantons. It's flat space with this flux. And there's also the axi-dilaton has a non-trivial quadratic form. So it's kind of actually, and for those of you that No, you can kind of uplift this to 12 dimensions, and there is a kind of a plane wave geometry in 12D, analog to plane waves in 11D. But okay, it's not very important. But now, what we built was the back-reacted geometry. Once you put this n d instantons, it's asymptotically to this, but there's also the back reaction of this n d instantons because we're taking n large, so in this tooth limit. Okay. And so,
where do you put these d instantons at r equals
well,
0?
if you put 1, it will just go to the center. You see, because the action of 1d instanton is basically tau. That's the first term.
But
so it will want to minimize this.
What source is this C2?
This is your background. So you put it from infinity. It just goes through. It's like putting an electric field that just goes through. The charges are at infinity if you want. So this is a deformation you put at infinity. And now on this deformed background, you put the d instantons, and they, if you want, they polarize because they feel the effect. So these fuzzy spheres correspond to actually polarized d instantons into two spheres.
I'm a bit worried that somehow this background is singular before when you started putting d instantons. Is it singular in any way?
No.
There's no singularity?
No.
Because you wrote 1 over r to the 4th, so when you go to r equals 0...
No, but that's an expansion at r equals...
But if we go to r equals 0, is there some big correction or not?
No, sorry. What I'm writing here is the asymptotic behavior of the exact geometry. Okay. So I'm just saying asymptotically it goes to this, which corresponds to the background, and then there are corrections that go inside, but we control all of those, and that's what I'm going to explain now, how to write the full form of the back-reacted geometry. Okay, so that's a long computation. Okay, we follow previous work on this finding supergravity. So we're looking for supergravity solutions which are supersymmetric and have an SO3, so they have a 2-sphere, and have an SO7 symmetry, so they have a 6-sphere. And so there have been previous work where people studied things with ADS2 and S6, or with S2 and ADS6. And so it's some kind of analytic continuation of that. So my student, Antoine Vunier, did a great job. I mean, I will explain why I trust his final results, but the hardcore supergravity calculations are hard for me. So, what is the geometry? Well, the exact geometry involves not just these 3 fields, so you also have to consider tau bar, for example, where you put here the complex conjugation. There's also, besides DC2, there's also Neveu-Schwarz 2 form that is turned on, so it's generated by the back reaction. And, well, I won't give you all the formulas, they are explicit. Let me just perhaps write the form of the metric so that you have an idea of what kind of, so there's, just by symmetry, you know that there should be functions of rho and z. And then you can choose coordinates z and rho so that the metric is exactly flat in this plane, z rho, okay? So that's a choice of coordinates. And now you would have to determine all these functions. And I'll just give you the result. So all these functions and all the other ones I didn't even write are given explicitly in terms of a function, v of z and rho, a single function, which solves an electrostatic equation, okay? So that's how this works. It's similar to other examples. For example, the very close, it's already dying again. Maybe I'm not writing properly. I killed the pens too fast. Let's see. So let me just state how it works and then answer some questions. So you write R4. So this is an auxiliary R4, has nothing to do with the real geometry. And you write it like that. There is a dz, and there's d rho square plus rho square d omega 2 square, okay? So this R4 has nothing to do with R10, okay? It's just a way to build this function. It's an auxiliary space. And so you write this metric like that, and you look for functions that solve the Laplace equation here, okay? So I've even be very explicit so that it's not confusing what I'm saying. Okay, the Laplace equation is just that. 2 over rho d by d rho v equals 0. Okay? Okay, that's a simple equation, but what about the boundary conditions? That's usually the problem when you do electrostatics. So here the boundary conditions are interesting. Let's see. So you have rho and z. What you do? You ground this plane. Okay, so this I don't know. Is it like this? It's grounded. V is 0 there. Okay. And then another thing you say is that when v very far away, okay, when this r, when both z and rho of the same order become large, v has an asymptotic expansion which involves this omega. That's how the omega enters. Well, that the number doesn't matter. So yes, just a second. I'm really saving you the most I can, I think. I'm trying, Slava. Good. And now you put some disks here. Okay, so I'll focus on the trivial vacuum. So there's just one charged disk. Sorry, charged conducting ball. So this is a conductor conducting ball with charge equals n. Okay, so that's how the parameters enter. And then you see there's a parameter which is the radius. Let me maybe call it capital R. The radius is fixed dynamically such that the electric field at the tip vanishes. Okay? So if you just fix the radius, usually tips have infinite electric field in electrostatics. So here you change the radius until there is no infinite electric field. Okay? That's how you fix the radius. That's how this electrostatic problem is solved. So this is exactly the same logic as Lin-Maldacena geometries, which give you the vacuum of the BMN model. Okay? Basically, for them, it was R3. That's the only difference. They were solving electrostatics in R3.
So are you ignoring alpha prime corrections, or?
No, this is just the solution in the supergravity approximation. Yeah. Then you can ask if the supergravity approximation is valid or not. And if you work in the 't Hooft limit, it's valid everywhere except far away, where curvature corrections are big. So there's a parametrically large region that grows with the 't Hooft coupling where you can trust supergravity.
Is there an easy way to understand why the Never-Schwarz B field is turned on?
Can you repeat the question?
Is it easy to understand why there's NS flux?
Why there is NS flux? I don't remember now if there's an easy. But let me think about that. I don't know. But yeah, to solve the full supergravity equations, you need them. But there must be a way to understand why is it sourced from the. I don't know if it's some Chern-Simons term or if it's really directly. Probably that. Yeah, that's sources. Okay. Sorry, I lost a bit. What I else want to say. So the geometry. So now, okay, you solve V, but then what is the geometry? So I told you the geometry is R10, far away, and as you go inside, you get non-trivial topology. Okay, so because here, if you just look at the map, you will see that on this axis the S6 collapses to 0. On this axis, the S2 collapses to 0, and also on the disk, the S2 collapses to 0, but smoothly. It's like end of the geometry. So in particular, if you draw an interval here, that's a closed tree manifold. So if you take this segment times S2, the S2 closes off there, and so it's like an S3 if you want. And there's also closed tree manifolds here, sigma 7. And so you can measure fluxes on this, and they are not zero. Okay, so there's a non-trivial dual geometry. Okay, any question about this? They are dissolved, right? Where are the D3 branes in ADS 5 cross S5? It's the same. They are, yeah. Yeah, but if you move to global coordinates, where are they?
But you're saying this is already the near horizon geometry?
Sorry?
This is the near analog of the near horizon geometry, and not the.
This is the analog of the near horizon geometry. Yes. Well, although here you see, since supergravity approximation breaks down as you go far, you don't really. I don't know how to write the solution. That would be the analog of including the asymptotically flat region. Yeah. Okay, so I gave you some details, not too many, but the point of this whiteboard was to show you that we know these geometries very explicitly, okay? If you want the other vacua, you put more disks, so we have one geometry per vacua, okay? This I did not emphasize, so I'm advocating a strong form of this duality, which is, at least in the 't Hooft limit, around each vacua, around each minima of this potential, you can have a self-consistent model, because there are barriers between different minima that grow with n in the 't Hooft limit. And so I expect that each minima has its own gravity dual, and you don't have to, in the 't Hooft limit, there is no tunneling. There's no whatever. Tunneling doesn't even make a sense here, but you can make sense of the model just within one minima, okay? So that's why I'm giving you geometries. We found, and the fact that we found geometries one per each vacua is evidence for that. Okay? If you prefer a more conservative approach that the integral was over everything, so you have to consider all vacua and see which one dominates in which parameter, I encourage you to read the last paper of Sean Hartnell and Liu, where they actually studied the competing vacua. They even did some Monte Carlo, not in the full model, but in the localization integrals that are left when you do localization, as I will briefly summarize here. And they see an interplay where in some regimes one vacua dominates, in some other regimes you have but this is, I mean, they're doing finite n, so I claim as you increase n, they will start to get stuck in vacua just because barrier grows. Okay, so as I promised, now let me explain you. The evidence for this, you could take it, I mean, if you are very experienced in string theory and building solutions, maybe this would be enough to convince you that that's the dual. That's just by have the right charges and the right symmetries and match. But now I want to give you an evidence that is more quantitative, that like the sum, I will derive this equation for this setup just using SUSY localization, okay, from the matrix model. And that's why I am so convinced that my student that did the supergravity part and the one that did the localization part, they both did their work very well, okay?
So is this string theory, is there a region where it's weakly coupled?
Yeah, so here...
so the dilaton is small there?
The dilaton is small here, yeah. If you work in the 't Hooft limit, yeah.
How do we use this gravity description to compute something?
That's a very good open question, unfortunately. I mean, you can compute something, but the problem is that infinity, I mean, this is not asymptotic ADS, and so the dictionary is not worked out in detail. I don't know exactly what computation I should do here in this geometry to match some particular correlator in the. So that's, I think, something that some people started thinking about, and but it's still not done. Yeah, that's important. Okay, where I want to go here, yes. Let me try this one. So I'm confused about the time. Here it says 34, but for sure I don't have 34 minutes. So I subtract 15. Okay, that's okay. Yeah, so let's, oh my God. Let's do. So, if you do SUSY localization carefully, so again, this was Adrian that is here that did this computation in more detail. So, the idea is basically there was a similar model in quantum mechanics, for example, BMN, and there was a series of papers by Hassan and collaborators where they did localization, and they found the same similar formulas for the BMN quantum mechanics. So here this was a generalization of that, but there is I mean, seriously, a series of many non-trivial steps, which Adrian says they all are obvious, that's the thing you have to do together. To me, it looks a bit arbitrary. They look correct, but why the choice was that, I'm still not convinced that's the best way. But in the end, you can write a partition function like that. It's just a sum over partition functions associated with this vacua. Maybe I should call, yeah, let's call this this representation curly R, let's say. Let's say this curly R. And that's an exact formula. So here, as I said, I will focus on the trivial vacuum. So I will just give you the formula for R0, let's say. And I will give you the formula already for not just a partition function, but to some observable, because we care about observables. So the observable that we can compute is this combination. Okay, using localization, we have to take a combination of the first 3 scalars and the last 7 scalars with this I. So that's the type of, I mean, of course you could also take first x3 and the post here and x2, but then it would all be 0 because it will be charged under an SO2, which is a symmetry. So this is not 0, and it can be computed with localization. So I'll just write this formula. So how is this formula, how does it look like? Well, okay, there's of course the normalization. So this is in the R0, it's an integral over n particles on the real line. The average is just the moments of the distribution of these particles. And what is the weight? Well, there's a Gaussian weight. Thanks, small n. Omega to the 4th, some numbers, some. So here, there's a Gaussian weight. And yes. No. Thanks, Peter. Yes, it's moments, yeah. And then there's a two-body interaction between these guys, okay? Product over all pairs, okay? Different from J. And this two-body interaction is some explicit function. So there's one feature which is important. There's a 0, so it means it's repulsive at short distances. Okay, this is a bit like the van der Monde determinant. But then there's some slightly more complex structure, but it's just a rational function. Okay. So that's it. So you should have asked, maybe some people have asked me in the past, but what does it mean you do localization? You already have a matrix integral. That's what usually localization takes you from a field theory, from a path integral to a matrix integral. Okay, here we already started with a matrix integral. So what are we doing? Well, still it's a matrix integral over n square variables, and we go down to n. So that's already a big simplification. Moreover, here everything is positive, so there's no sign problem anymore. So this one, that's where Sean, Artnell, and Liu did Monte Carlo. It's with this measure and then the analogous measures for the other representations. Okay, so that's the equation. I'm not gonna say more. Now, how do you solve this? Well, exactly, it's an integral, it's hard to do, but of course you can take the 't Hooft limit, so you take the large n limit, and then you think about these particles, you think about the density of these particles, right? So you introduce some density, which is just a sum of x minus mi, I from 1 to n, and think of this a of x as some collective coordinate, which is the density. And then you try to rewrite this matrix model using this collective coordinate and find the saddle point. Okay, the usual large n techniques for matrix models. Okay, so if you do that, something remarkable happens. Is that the equation you find for a of x, it's exactly this equation. And what is the identification? Well, take this charged disk. So this is a, okay, so here each point on this auxiliary R4, each point along this line is an S2, right? So this is a ball in R3. Okay, so I can draw a ball in R3. And now pick some axis through the center, call that x, and cut at fixed x, right? And compute the charge density on that. So the charge density here, you call it a of x. That's the map, okay? So you see, it's a bit strange because it's a spherically symmetric distribution of charge. So you should, I mean, we're used to describing that as a charge density depends on the radius. But here, you trade that information, that function of the radius, by this function, by slicing by planes perpendicular to the x-axis. It's the same information. And if you do it like that, then this a of x becomes the density of eigenvalues, or the density of these particles in the large n limit. Okay, so that's when I saw this identification, I was happy that, okay, my students found this equation in completely different ways and everything agrees. So that's why we are confident, or at least I am confident, that this geometry is the dual to this model. Okay? Although we don't have many other tests of many other observables. Okay, it would be good to have more. Questions, comments? I have 10 minutes, yes. Not everything. You have to, let me think. Yeah, for sure, this thing, yes, this repulsive thing at short distances. I don't know off the top of my, you say if I just set all this to constants, if that's enough, for example. I think that's too brutal, but maybe Adrian remembers better. I think that's too brutal. I think you need a bit more about this potential, this two-body interaction.
Yeah, so we had an identification of parameter in the gravity dual, right? By matching the n with the number, with the flux of the D1.
Sure, sure. That's the string theory part, yeah.
And in the matrix side, we discovered again this relation, I think. So there was some coefficients that were important. That was a non-trivial check. But yeah, I don't remember exactly. Yeah, maybe if you rescale everything by lambda, maybe it's fine. But yeah, I don't know.
And then what about the boundary conditions?
Boundary conditions for what?
So there's some non-trivial boundary condition.
Yeah, so here the problem appears in terms of V. Here you don't see any V. So what you have to do is you take some charge distribution, then you just compute the potential it produces, right? Because it's just solving. I mean, each charge produces a Coulomb potential, just sum that. And then you see what force that potential makes on the charge, because they can move. And that's your local equation for the charge density here. And that's the equation we derive from this side, that you just get an equation for A of x. That A of x depends on A at different positions through some kernel. So this kernel comes from, it's not obvious, right? But that's the work we did to show that that kernel corresponds to solving this potential.
Joao, can I ask? So you said at the beginning that you just said, I'm just going to consider x equals 0 vacuum.
Yes.
Here to match, does it mean that the other vacuum is large n, is suppressed at large n? Like there's some condition, right?
As I said, I am working vacuum by vacuum. I take this equation is true, is a mathematical identity. But what I'm going to say is that I will never do sums. I say each ZR is a world in itself. And I match observables for each ZR.
And omega, so omega cannot be 0, is that right?
Sorry?
Omega cannot be 0?
Good, I was almost forgetting about that. It's an interesting question. What happens if I send omega to 0? Okay? That's another funny story. As a good physicist, I thought, well, send omega to 0, go back to IKKT. That's what, it's in our face. Adrian computed the partition function, send omega to 0, it diverges. Now, Adrian, what are you doing? Doesn't make any sense. Everybody knows the IKKT partition function is a number, okay? So if you do this action, the partition function of IKKT is a number, it's a finite integral, okay? Not everybody knows, I learned recently, but yeah, I knew that was it. In fact, there's a finite set of moments of x that are finite, okay, up to a certain power. So you can think that the distribution just with pure IKKT decays power-like. So you can take a finite set of moments, and then at some point, they become infinite. So, okay, I was expecting to recover that. Adrian does the computation, infinity. No, it comes 2 days later, no, it's still infinity. I think you're wrong, it's infinity. And then we found out that indeed it doesn't go back, okay? So then he convinced me, and it's a bit subtle to explain, but maybe I can briefly try. So, yeah, so I'll try to be brief, but it's like that. Bosonic of x, Pfaffian of x, and okay, here there's also the omega, right? And here omega also appears in the Pfaffian. So if you set omega to 0 in the Pfaffian, you just get IKKT. So then here, of course, it's safe. If you send omega to 0, you go back to IKKT. The problem is that the terms inside the Pfaffian that are multiplied by omega are multiplied by higher powers of x. So the Pfaffian enhances the divergence. Okay, so as you send omega to 0 in the bosonic, that removes the Gaussian suppression, right? This Gaussian in x, and the psi terms are multiplied by omega, so they are going to 0 just by that factor. But what multiplies omega is a higher power of x, so in the limit you actually get infinity. Okay, this thing wins. well, I don't know, it's a bit technical to explain like that, but so the crucial point is that omega to 0 limit of this is not IKKT. Okay? If you want to get IKKT, we have some proposal picking some residues instead of just taking the naive limit, which we think it works. But okay, that's some trick. The physics is just different. The physics is just different.
Is it because you Is it because you need to do the sum over R?
No, it's not related to the sum. I mean, even if you just are on the trivial vacuum, it will diverge. Yeah, it's actually the trivial vacuum that diverges.
But when omega goes to 0, we should no longer think about representations of SU2, right?
Yeah. So that's what I'm saying. I don't think about even around just this trivial vacuum.
But instead, there's a modulo space, right? There are flat directions of the integral, right? At omega equals 0.
You say these minima are very close by.
Aren't there any matrices that commute are saddle points, right? When omega
here.
Yeah.
Right. But then you would say IKKT should diverge. But it turns out it doesn't, because these valleys of commuting matrices, they don't have enough volume. You see, like in this higher dimensional space, you still have, they are integral. The volume inside those around those valleys is finite.
But I guess you still have to integrate over them.
Yeah, you integrate over all x's. And even if the potential is 0, what I'm trying to say is, well, let me do it like this. No, that's not true. Only in this sum, only the trivial vacuum, no, not true. The trivial vacuum diverges more than all the others with a higher power of omega. And then the others diverge less until sums don't even diverge. The picture is like that. I can tell. Actually, I was going there, so you can ask me again if it's not clear. It's the same. I'll do it here in the middle. Okay, I have less than 10 minutes, so let me finish with some discussion, because, okay, I presented the model, but the dreams in the beginning were very ambitious, and we seem to be very far. So at least I want to motivate you to have better ideas in the direction of the dreams in the beginning, okay? Okay, so, okay, let me just write. So, what is the main question? Okay, from my point of view, the main question is, okay, I have a model, finite integral, okay, I need to take large n, but it's completely well defined. I can give it to a mathematician, and I claim in some limits, so let's say the 't Hooft limit for concreteness, strong 't Hooft coupling, it's given by this geometry. So where are the supergravity fields inside this model? Right? That's what we want to understand. Where are they? One way to think about this model that I particularly like is like a gas. Okay, so there's no time, so it's like statistical mechanics. So we need to understand this gas, and this gas seems to have a new phase of matter which is described by gravity. So let's try to understand what's special about this gas. So I'll be very naive. So let's say I take the diagonal elements. So the diagonal elements live in R10. So I can put points in R10. Okay, A equal 1, 2, n points in R10. And then I have the off-diagonal elements, x, a, b, mu, with a different from b. Well, these are actually a pair of, it's complex, so AB and BA are complex conjugates, so it's like two real degrees of freedom. So you can think there are some degrees of freedom that are also just a position in R10, but they are associated with pairs. So maybe you draw some lines, or you think they are open strings in some sense. Okay? So these are the degrees of freedom you have. And they are in an harmonic trap. Okay? So there's this quadratic potential that has an extent 1 over omega. It's the harmonic trap where they live. So they are not free particles. They're good statistical mechanical systems. They are in a box. And we know two easy limits. So if you send omega to infinity, so the trap becomes very, very small, then they become free particles. because, as I said, when omega goes to infinity, the quadratic terms dominate, interactions are subdominant. So this gives you n square free particles in R10. Okay, n square, in the sense that the particles associated with the pairs also become free particles. The other limit we also understand. In this limit, what happens is that the particles associated with the pairs, the off-diagonal elements, become very massive, so in the sense that the quadratic term grows because of this commutator square, and what you get is just n free particles. So just the diagonal elements live as free particles in this harmonic trap. And that's already enough to explain why the free energy diverges. It just diverges because you have n free particles, and as omega go to 0, you get bigger and bigger volume. It's just a volume divergence. There's nothing deeper. And you see, and the fuzzy vacua correspond to bound states. So if you make the irreducible, it means you take these n particles and you make a bound state. So the divergence is much smaller. It's just the center of mass that can move. Okay, so the power of divergence is the volume, and that is just related to know how many bound states are there. Okay, so that the one that diverges more is when you don't have bound states. Okay, so my challenge to you is, you know the energy of the configuration, if you want, right? It's given by this. There's some particles in an harmonic trap. They are interacting. And there is a phase which are described by gravity. So is it the density of particles? Is it some effective field that describes the long-range interactions that is going to be, I think that's the challenge for us, understanding how that supergravity description emerges from this special gas, and what is special about this gas and all that. Okay, that's a dream. I'm already below 15, that's a bad sign. So then let me just finish saying that one way of addressing this question is to think about similar models. Okay, so for example, tomorrow Arish is going to talk about only purely bosonic models. Okay, so you drop all the fermions, you just keep this commutator square, and you study what these bosonic models with this commutator square interaction, how do they behave, okay? In different dimensions, not just 10, but you take 2, 3, 4, okay? And in fact, I encourage you to go because d equals 2 is very special, and then 3 is above 2, things change. But so there is some interesting physics already happening in the pure bosonic models. And I also encourage you to go to Adrian's talk, where he's gonna keep supersymmetry, but change dimension. Again, not going just to 10, but there are similar models with commutator square interaction for bosonic, so Yang-Mills type matrix models, in 6, 4, and 3, which are much more friendly to, say, Monte Carlo or other studies. And it's unclear, at least at the moment, why some of these models are better than others in the sense that we can find supergravity. Okay, so we only know the dual for this one, because that's the string theory offer, but maybe the other ones also have interesting physics. Thank you very much.
Any further questions?
Thanks. Okay, I'm just curious that if there's no supersymmetry, you just consider the bosonic model, can you still get Einstein gravity dual?
I don't think so, but you should come tomorrow. No, but they will not find supergravity duals. And but I can ask you the question to you. What about our world? Is there a UV completion of gravity in our world? There's no supersymmetry at low energies, so supersymmetry cannot be so essential.
But in our universe, it's not an ADS as well, right?
Okay, but what? This is also not it, yes, that's true. Well, anyway, it's an open question. If you think supersymmetry is essential for supergravity, maybe you're right. I just don't know a very strong argument for that.
Yeah, I mean, before go to the gravity dual, so just check about the spectrum. So here, if you have SOSU, you can have large gap in the spectrum, in the single-chip spectrum, right? And without
so here, I mean, I don't know in what sense you reason. I mean, here there's no time, so there's no Hamiltonian, there's no direct notion of energy. This is statistical mechanics. It's just equilibrium. So the way, I mean, but okay, then it looks too boring, but you can still do interesting stuff because you can probe it by, say, changing fields at infinity. Like, okay, you have the gas in a box and you want to know if I change the side of the box or if I put some field, how does the box re-equilibrate, right? So that's the kind of physics that we have access here because we can either deform the model or measure different correlations, different observables about this model. Okay? For example, you can ask, what is the distribution of these guys, right? When you integrate all the others, what is the distribution of the first element, one diagonal element, right? That gives you the shape of the gas. And then you can ask, suppose I don't integrate out 2 and I integrate all the others. Then you can also have access to 2 particle correlations, things like that, right? So those are the observables here. There's no...
Okay, thanks.
So that by lack of time, I didn't list that, but there was a point here. I think the dictionary, it's not well understood, so we should understand better. So for example, by analogy, even yesterday we saw, right, this I1, let's say P, right, and you contract with some null vector, right, to make symmetric traceless tensors. Just a second. Let's call this operator defined like this. I think by analogy with the other examples that this will be in supergravity, that correlation functions of this guy will be computable by supergravity, but I don't know precisely how. What combination of bulk fluctuations corresponds to these fields? So that I think would be very interesting to understand.
But do you think it's only gauge invariant operators?
So as I said, I don't like to use the word gauge invariant, but here you see the trivial vacuum is SUN invariant. So, I mean, you could look at correlation functions of non-singlets as long as there is a singlet in the whole product. That will not be 0. But the overall distribution is SUN invariant, so it will project on the singlet observables.
Yeah, so I have a question. So the string theory is, well, it's an example of a theory of quantum gravity, but it's a very special example in various aspects. First of all, it's a weakly coupled theory of quantum gravity.
Well, I also don't know what does it mean, a strongly coupled theory of quantum gravity.
Well, I mean, string theory has a parameter G, and
you
may not think that every theory of quantum gravity is obliged to have this parameter. String theory has D-branes, and D-branes play a crucial role in all these games that people are playing to construct these duals.
Yeah.
Now, so do you expect that the lessons you are going to learn, they will apply to any theory of quantum gravity, or maybe there's like a special class of theories of so could you like formalize what should be the requirements? Because you know many, I don't know, but you know many examples of when people played similar games and succeeded. Can you kind of crystallize all those examples into for what should be a theory of quantum gravity in which this sort of games can be played? Suppose you have a theory of quantum gravity which doesn't have D-branes, doesn't have D-instantons. Would then this sort of games would be applicable to that theory of quantum gravity?
There's several answers that come to mind. So if at some point you seem to ask about some finding some patterns in the examples we know.
Yeah.
To some extent, I see the swampland program as trying to do that, or whatever they call the string lamppost principle, right? They try to see in all the string theory constructions what are the patterns that are universal. So that's to some extent already happening. I'm not going in that direction. It's one direction. Here, I was taking this idea that there is some quantum system that should have, so this, from the effective field theory point of view, it seems like a robust phase of matter. That, okay, you have a spin 2 massless particle, and that implies for you that you have GR plus curvature corrections. It's weakly coupled in the IR, right? If you have a big system, the gravitons are weakly coupled, so it's a good effective field theory. So why is it so hard to find quantum systems that follow to this? It looks like robust from the IR point of view. So since I don't know how to invent them, I'm trying to look at the examples that exist, the simplest possible, to find the patterns that lead to that. I think if we could do that, then we could do model building. We could apply, let's change that, this doesn't kill the gravity. But this is like speculation on top of speculation.
This is circular because your example has already been constructed from a theory of quantum gravity, which was very special. It had d-branes. So how can this be? How can you learn any general lessons?
Well, if I now remove, so I erase this term. Is it still okay?
As you said, most likely.
Then if I erase this term, it's not string theory anymore. There's no, I don't know how to do that in string theory. Maybe someone can. I don't know, but this was what I have in mind.
So my bet, and I think your bet as well, that no, it's not going to work.
Okay, we'll see.
So perhaps let's give John the last word, and then we should conclude.
Mark, I think I was also waiting for a while. So.
Sorry, I wanted to respond to what Slava said because I think I disagree with you. I mean, Joao was saying that this is a theory of quantum gravity, and there are no d-branes in that. It's just an integral, right? I mean, the way he figured out that was the theory of gravity, he used string theory.
Bonelli, yeah, IKKT plus Bonelli.
So I just wanted to ask, so here you gave this intuitive picture in which there's particles already in the same number of dimension in which gravity then emerges.
That's true.
But it looks a bit strange. It looks like the graviton then should be a composite, which we normally don't believe it's the case. So I just wanted to understand how that works.
Yeah, I have mixed feelings about that. Yeah, it's true. But even in n equals 4, right? It's the scalars are 6. So if you add the dimensions, the 4 dimensions of the CFT to the C, you still get 10. So it's here. I mean, if you take this at face value, what's happening is that these particles, once they back react, they form a non-trivial geometry where they are, but it's already 10 dimensional. It's kind of a, so
there's already gravity if they back react, right? So gravity there is.
No, what I'm saying
Sorry
is,
guys, I really think that we're a bit out of time. People are hungry and probably still drunk from last night. So let's thank Joao again and continue our discussion over lunch.
Thank you.